This is 3 or more contiguous p orbitals. This molecule is conjugated. Hey, OChem Ninjas. In this video, I'd like to talk about conjugation. What is conjugation and why is it so important in organic chemistry? Conjugation is one of the key early skills that we need to master in organic chemistry if we want to be able to succeed as true OChemNinjas. Conjugation is the foundation for resonance and helps explain a bunch of concepts in organic chemistry, such as relative acid and base strength, carbocation stability and its influence on SN1 and E1 reactions, why some nucleophiles are stronger or weaker than others, why most organic chemicals are colorless molecules but some have a color, and concepts like aromaticity and electrophilic aromatic substitution. So we are going to see conjugation come up a lot in this course. So let's start with a definition of conjugation. Conjugation occurs whenever you have 3 or more contiguous p orbitals. And just about every syllable in that definition is extremely important. Conjugation involves p orbitals, overlapping p orbitals. If we're going to have conjugation, we need to have unhybridized p orbitals in the molecule. We don't consider a molecule to be conjugated until we have 3 or more of those p orbitals that are contiguous to each other, and they must be contiguous. Contiguous means touching. They must be on adjacent atoms so those p orbitals can overlap. For example, if we just have an oxygen with a negative charge, this molecule is not conjugated. There are no p orbitals in this molecule. If we just have an isolated alkene, this molecule is also not conjugated. It does have p orbitals. The pi bond is comprised of 2 overlapping p orbitals, but only 2. We only have 2 p orbitals, and so we would not consider this molecule to be conjugated. Even when we do have more than 3 p orbitals, the molecule still may not be considered conjugated. Here we have 2 pi bonds, so we have a total of 4 p orbitals, but they are not all contiguous. We have 2 p orbitals on carbons 1 and 2, and then a gap, an sp3 hybridized carbon, and then 2 more p orbitals on carbons 4 and 5. Because all the 4 p orbitals are not contiguous, we would not consider this molecule to be conjugated. A molecule with an allylic cation is conjugated. The pi bond is made by 2 overlapping p orbitals, and the carbocation is sp2 hybridized, and it has an unhybridized p orbital as well. Each of these 3 atoms has an unhybridized p orbital, and they are all contiguous. This does fit our definition of a conjugated molecule. Conjugation is not limited to positive charges, and it's not limited to 3 atoms. Here we have 5 atoms in conjugation. We have 2 p orbitals on the pi bonds, we have 2 p orbitals on the other pi bond, and the lone pair lives in a p orbital on this central carbon, giving us 5 contiguous p orbitals in this molecule. In fact, we don't need charges at all. 2 consecutive pi bonds would be considered a conjugated molecule. Each pi bond is the overlapping of 2 p orbitals, and when they are consecutive like this, we have 4 consecutive carbon atoms, all with unhybridized p orbitals. This is 3 or more contiguous p orbitals. This molecule is conjugated. There are innumerable examples of conjugated molecules, but I will end with this one. This one's kind of an extreme version of conjugation that we've been talking about, but it is definitely conjugated. There are 6 atoms in each benzene ring. Each atom in the benzene ring is sp2 hybridized, therefore it has an unhybridized p orbital, so each benzene ring already has 6 unhybridized p orbitals on contiguous atoms. A benzene ring by itself is conjugated. In this molecule, the conjugation extends even further. The benzene ring is adjacent to the pi bond with 2 more p orbitals, which is adjacent to the carbonyl, which has p orbitals, and another pi bond with p orbitals, and another benzene ring with 6 p orbitals. This entire molecule is fully conjugated. The only reason I bring up such an extreme example is to say that as you get more and more conjugation, eventually you get to a point where the molecule takes on a color. This molecule happens to be a yellow color. Why it has a yellow color is a bit beyond the scope of this course and has to do with UV-vis spectroscopy, but check out the linked video down below if you'd like to know more about why conjugated molecules take on a color. Instead, the reason for this video is to talk about why conjugation is an important concept in organic chemistry. And it's simply this. Conjugation makes molecules more stable. Conjugation is the basis of resonance. Conjugation allows us to draw resonance contributors. Resonance allows us to spread electron density out over a larger volume, and when we spread electron density out through resonance because of conjugation, that makes those electrons more stable, and it makes the whole molecule more stable. Conjugation makes molecules more stable. To demonstrate this, I want to compare and contrast 2 molecules. I have one molecule drawn here. Propene. It has a pi bond and a CH3 group on the other side. If we draw the orbital picture for this molecule, we assume that the molecule is sticking out perpendicular to this board. We can look at the p orbitals in this molecule. If you need help drawing orbital pictures of molecules, watch the video that I have linked down below on how to do just that. This molecule shows us that the pi bond is comprised of 2 overlapping p orbitals. The pi bond is the sharing of those 2 electrons between those 2 p orbitals. But the CH3 is an sp3 hybridized atom, and so it does not have any p orbitals, and so it cannot share any electrons with the pi bond. This molecule is not conjugated. These electrons are confined into the pi bond between those 2 carbon atoms. Electrons don't like to be confined in a small volume. If you want to watch the video about confining electrons to a small volume, I also have a link to that one down below. These orbital pictures are nice, but they're an approximation. We have software that allows us to calculate what the molecular orbitals might actually look like for these molecules. And if we bring up the molecular orbital picture for this molecule, this is the same picture just rotated in the 2 different versions. We can see that the pi bond, the pi electrons, are confined between those 2 carbon atoms, and there's a gap between the CH3 carbon. The CH3 carbon is separate from the p orbital. And I want to contrast this non-conjugated molecule with the allylic cation that is conjugated. Here we have the pi bond with the 2 p orbitals between the 2 carbon atoms, and we have a carbocation, which is sp2 hybridized, which has an unhybridized p orbital. That gives us 3 contiguous p orbitals in the molecule. Again, we can look at the orbital picture for this molecule, and here we see something really interesting. We see that there are p orbitals on each of the carbon atoms. That way we can take the electrons that are shared between the 2 carbon atoms and share that electron density with the carbocation carbon. The p orbitals overlapping allow us to spread that electron density out over all 3 atoms. Spreading that electron density out over more atoms allows those electrons to be more stable than they would otherwise be if they were confined in a smaller volume. But we see a really nice illustration of that when we use the modeling software to model what those orbitals look like. Look at that pi cloud now. Notice how that pi cloud extends over all 3 atoms. The orbital expands its volume to fill all 3 atoms. The electrons are not confined between these 2 carbons. They're able to spread out between all 3 of those atoms through conjugation, through resonance. That's why conjugation is so important in organic chemistry. With contiguous p orbitals, the orbital volume expands so those electrons can spread out over a larger volume. And this has major implications in all aspects of this course. It explains why we can draw resonance contributors and why drawing resonance contributors makes molecules more stable. It explains why some conjugate bases are more stable than other conjugate bases, and therefore why some acids are less acidic than other acids. It explains why some carbocations are more stable than others and why we can do SN1 with some molecules but not with others. It explains why certain photons of light are able to excite electrons to a higher energy level and why some organic molecules take on a color when you extend the conjugation over a large enough volume. It explains why some molecules are considered aromatic while other molecules are not, and why those aromatic molecules are so much more stable than we'd otherwise expect. Don't worry if you haven't gotten to all of those concepts yet. You will as you go throughout the course, and I've got videos linked down below that you can come back to when you get to those sections. The key concept to remember from this video, conjugation is when we have 3 or more contiguous p orbitals, and conjugation makes molecules more stable.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.